Hi, everybody. I'm Dr. Gray. I wanted to give you instructions on how to deal with the math that you're going to encounter in this week's experiment. Now, this titration is a little bit different from titration that we've previously done. What makes this different is a number of different things, one of which is we're not dealing with a strong acid. Instead, we're dealing with a weak acid. In addition to that, we're dealing with a mixture of acids. Okay, so the solution that we're going to be working with, our juice solution, is actually a mixture which, as you can imagine, has a number of different acids. This has both citric acid and vitamin C. Vitamin C is also known as ascorbic acid. Now, for this experiment, what you'll need to know about these two acids is that citric acid is what's known as a triprotic acid. What that means is this is a molecule that can donate a total of 3 protons. Vitamin C is what's known as a monoprotic acid, and therefore it can donate a total of 1 proton. Now, combine these 3 protons from citric acid and this 1 proton from vitamin C, we are going to neutralize them with a strong base known as sodium hydroxide. Now, for maybe something that you've seen in your Gen Chem 1341 class, you've probably talked about ionic reactions. When it comes to sodium hydroxide, NaOH, arguably all that we care about in a titration, in this specific acid-base titration, is that hydroxide ion. So one hydroxide ion will neutralize one hydrogen ion. Therefore, if we have a total of 4 hydrogen ions that we need to neutralize, we need a total of 4 hydroxide ions. So what we end up with here is a ratio of 4 hydroxide ions for 4 hydrogen ions. Now, for the purposes of this experiment, here's sort of the calculation that you need to do. Let's say hypothetically, you do this experiment and you add a total of, let's say 13.65 milliliters of a sodium hydroxide solution. That sodium hydroxide solution has a concentration of 0.1 molar. So effectively, what you need to do is you need to figure out the number of moles of sodium hydroxide that you're adding. So what we need to do first is take our volume in milliliters and convert it to liters. Now, there are 1,000 milliliters in 1 liter. So what we're going to do is we're going to move our decimal place. Since we're talking about converting from liters or milliliters to liters, we're going to move our decimal place 1, 2, 3 places. So we're going to end up with 0.01365 liters of sodium hydroxide that were added. As soon as we have the volume of sodium hydroxide, we need to look at what's the concentration. Our concentration is 0.1 molar. So 0.01365 times 0.1 molar. If you remember that capital M, molar, is moles per liter. So we say 0.01365 times 0.1, and that will give us 0.00135 moles. So we are adding, in this titration, we'll say that hypothetically we had to add 0.001365 moles of sodium hydroxide or 0.001365 moles of hydroxide ions. Now, if we want to figure out the total number of, or the total amount of acid that we added, total number of moles of acid, what we can do is we can take this number of moles of hydroxide say, well, that look at our balance, or looking at our ratio, there are 4 hydroxide ions for neutralizing 4 hydrogen ions. So what we can say is that we have 4 acidic protons. We can say 0.001365 moles of hydroxide times 4 divided by 4 gives us 0.001365 moles of acidic or acidic protons. Now, that 0.001365 moles of acid is, you could look at this as 0.001365 is equal to moles of citric acid, which I'm just going to label Cit A, plus moles of Vit C. Now, the thing is, we have no clue what the amount of citric acid and what the amount of vitamin C is. But we know that those two amounts combine to give us this 0.001365 moles of acid. Now, that's what we determined from our first part. For our second part, actually, I think I can do this all on one page. No, I'll revisit. For our second part, we're doing a titration where we use IO3, potassium iodate, which KIO3 is potassium iodate, but we really don't even care about the potassium because that's a spectator ion. So I'm going to erase it. And I'm just going to label it as IO3 minus. That IO3 is going to react with a couple of different things. It's going to react with 5 moles of I minus from a solution of potassium iodide. It's also going to react, this is in an acidic environment, 6 moles of HCl, which I'm just going to label as 6H plus. So whenever you do this second part of the titration, you're adding the Ki and you're adding HCl to that solution. Then you're titrating in the potassium iodate. So what this is going to give us ultimately is it's going to generate 3 moles of I2 plus H2O. Now, this I2 right here, what that's going to do is that's going to do an oxidation reduction reaction with vitamin C. So this I2 is really what we want to produce. And I'm going to label reacts with Vit C, but not citric acid. So arguably you could look at this and say, well, if this reaction, if our second part will tell us the amount of vitamin C, then we can go back to this part and say, okay, well, if we can figure out the number of moles of vitamin C from part 2, then we can do, with deductive reasoning, say, well, we know the total amount of acid, we know the amount of vitamin C, therefore, here's the amount of citric acid. Okay, so here is a hypothetical number. So let's say that you do this titration, and what you find, and sorry, let me go ahead and wrap the second part of this up. So I'm going to erase this. When we generate this I2, it's going to do an oxidation reduction reaction with vitamin C, and it is going to produce something known as dehydroascorbic acid. CID. And so this is going to react in a 1-to-1 molar ratio. Now, for this purpose or for this experiment, that's all that you need to know about this. You need to know that this is a 1-to-1 ratio. Now, to look at some hypothetical numbers, let's say hypothetically that you do this titration and it takes you 22.6 milliliters of the KiO3. Again, we don't care about that K because this is an iodate solution. It's potassium iodate, but that IO3 is the only part that we care about. We then want to look at this reaction up here. Now, I've omitted quite a bit from here, but the important part is this right here, the relationship between IO3 and I2. Because in this second reaction, that I2 that you're producing will react with vitamin C in a 1-to-1 molar ratio. So what that gives you effectively is dimensional analysis that looks like this. Here is the amount of iodate, the iodate that you needed, IO3 minus. What you can then do, or actually, I'm sorry about that. One thing that I need to include is I need to do the math to convert this into number of moles. So 22.6 milliliters of IO3 with a solution that has a concentration of 0.001 molar. Convert this 22.6 into liters. So that would be 0.0226 liters. Multiply that by 0.001 molar. And that's going to give us 0.0226 times 0.001. That's going to give us 0.0000226 moles of IO3. So this is, you transferred from your burette 22.6 milliliters of iodate. That 22.6 milliliters of iodate, that solution has a concentration of 0.001 molar. Therefore, you added 0.0000226 moles of IO3 minus. Now we can get to the dimensional analysis and look at our ratios of our iodate to our iodine. 0.0000226 moles IO3 minus. We can look back to our balanced chemical, or to our chemical reaction that we're concerned with, and say that this is 1 mole of IO3 to 3 moles of I2. Okay. Now, we have to look to our second reaction there. Our second reaction tells us that we have a ratio of 1 mole of I2 to every 1 mole of vitamin C. What we are trying to figure out is how many moles of vitamin C are in this solution. So what we can do is say this part from reaction 1. I'm going to draw an arrow to it. That's where that ratio came from. Now, we want to have I2 in the denominator, and so now we're going to get this from reaction number 2. 1 mole of I2 reacts with 1 mole vitamin C. This part, reaction 2, I'm going to draw an arrow right up here. Now, we have all that information in, and what we can do is plug this in. 0.0000226 times 3 times 1 divided by 1 divided by 1 gives us 0.0000678 moles of vitamin C. Okay, so this number right here, what's the use of it? Well, the use of it is we can come back here and we can say we know the total amount of acid, the total or the combination of moles of citric acid and moles of vitamin C was 0.001365. We just solved for the moles of vitamin C, and that number was 0.0000678. And so what I can do is do a little bit of algebra to rearrange this and say moles of citric acid is equal to 0.001365 minus 0.0000678. I'm going to plug that in my calculator. 0.001365 minus 0.0000678. And I have solved for the moles of citric acid, which are equal to 0.001297. We want to write that in dimensional and proper scientific notation. We write it as 1.2. Let's see, I moved my decimal place. 1, 2, 3. 1.2972 times 10 to the negative third. And I was coming in with a total of 4 significant digits. So I'm going to stop at that right there. So I'll erase that number right there. Nope. 1.297 times 10 to the negative third moles of citric acid. All right. Well, I hope this was helpful. In order to figure out the number of moles of citric acid and vitamin C, you have to do both parts of this. We're not directly figuring out the number of moles of citric acid. Instead, we're figuring out a combination of the two, then directly figuring out the moles of vitamin C and saying, based on this, this is how much citric acid we believe to be present. I hope this was helpful, and I hope you have a good one.